Hello everyone, and welcome to your very first Programming Language Lab Explainer. I'll be acting as your helpful teaching assistant for today. Look, I know taking that first step into programming can feel incredibly daunting. If you've never written a single line of code in your life, honestly, take a deep breath right now, because you are in the exact right place. We're going to take this slow. Today, we're going to walk through exactly how to set up your digital workbench and write your very first C++ programs together, line by line. So grab a cup of coffee, settle in, and let's dive into this.
Here's a quick look at our digital syllabus for today's session. We'll start from the absolute basics, then get your coding environment set up, write your first real program, squash some bugs, and finally, we'll end by actually creating our own digital console art using C++.
Section 1, Welcome to the Lab.
Okay, let's lay down some absolute foundational concepts before we type anything. We need to understand how the English-like text that we type actually gets understood by your machine, because it's a pretty fascinating process. The crucial starting point is this. When you write code, you are creating what is called a source program. This is simply the initial, human-readable version of a program that you type into an editor and save as a file. And for C++, that file usually ends in .cpp. Now, I want you to think of the source program as your raw recipe. It's the instructions you write out step by step in a language that you and I can easily read and understand. But here is the catch, and it's a big one. Your computer's hardware, its processor, it has absolutely no idea what to do with this text. To your CPU, English words are meaningless.
And that is exactly where this next vital piece comes in. Because your computer simply can't read our C++ syntax, we desperately need a translator. And in programming, this translator is called a compiler. The compiler acts exactly like a master chef in a restaurant, taking your written recipe and translating it into a physical, edible meal that the machine can actually digest. More technically, it takes your human-readable source program and converts it entirely into the machine's low-level binary language, those millions of ones and zeros that tell the hardware exactly what to do. It's really important to grasp this. Without a compiler, your C++ code is literally just a fancy text document doing nothing.
Moving right along to Section 2, Setting up Code Blocks.
Now that we understand the theory behind source code and compilers, let's actually equip your workbench. We're going to install an IDE, which stands for Integrated Development Environment. The one we're using today is called Code Blocks. This is your all-in-one workshop where you'll write, compile, and test your code. Setting this up, especially if you're on Windows, is incredibly straightforward, but there's one massive trap you need to avoid. You'll head over to codeblocks.org/downloads and click on the binary release. Now, pay absolute attention to step 2 here. Make sure you download the installer that has mingw in the file name, something like mingw-setup.exe. Why? Because mingw includes that compiler we just talked about. If you accidentally download the basic version without mingw, you're going to end up with a text editor, but absolutely no compiler to translate your code, and your programs will never run. Once you have that mingw version downloaded, just run the installer and click Next right through all the default options.
Awesome. So once it's fully installed, creating your very first workspace is a total breeze. You just launch the program and navigate up to File, then New, then Project. You'll want to select Console Application. We choose that because everything we're building in this lab is text-based. No graphical user interfaces or buttons yet, just pure text in a console. Next, you'll select C++ as your programming language. Give your project a nice descriptive name and just hit Finish. Code Blocks is incredibly helpful here. It automatically generates a starter file for you called main.cpp. Now, let's open that file up and see how it builds our very first program.
All right, Section 3, your first C++ program.
So go ahead and open up that main.cpp file. We are going to completely break down this classic Hello World blueprint line by line. The goal here is for you to understand exactly why every single piece of syntax exists. I know it looks like an alien language at first glance, but stick with me, it's actually very logical. Let's look at the top section. That very first line, #include !iostream bracket. In C++, this is what we call a preprocessor directive. Basically, it's telling the computer, hey, before you do any compiling, go out and bring in the iostream library. That specific library gives our program the superpower to do basic input and output operations, like actually printing words to your screen. Right below that, we have using namespace standard. The STD stands for standard. This is a massive time saver. It simply tells the program to use the standard library namespace by default, which physically saves us from having to type out std semicolon before every single command we write later on. Then we have int main. This is huge. The main function is literally the front door. It is the exact entry point of your entire program. When you tell your code to run, the computer blindly searches for this main function and immediately starts executing whatever instructions you've placed inside those curly braces.
Now let's look inside those curly braces, because that is where the real action happens. We have this statement here, cout, which is pronounced cout, standing for console output. Right after cout, we use these two little less than signs. Those are called stream insertion operators. Think of them like a funnel or a conveyor belt pushing our text, hello world, straight to the computer screen. We then use another set of those arrows to push endl onto the screen. Endl stands for end of line, and it just moves your cursor down to the next line, exactly like hitting the Enter key on a typewriter. Finally, we wrap up with return 0. Remember how our main function was an int, short for integer? That means the operating system is expecting a number back when the program finishes. Returning the number 0 is the universal signal to the operating system saying, hey, everything went perfectly, we had 0 errors here.
That brings us to Section 4, compiling and fixing errors.
You've written the code, you understand what it does, so let's actually bring it to life. To do this in code blocks, we press the F9 key on your keyboard. F9 is the magic button. It tells the IDE to run the build and run command, meaning it summons your compiler chef to translate your text into machine code, and then it instantly executes it. If your code is completely flawless, if you typed everything perfectly, your build log at the bottom of the screen is going to reward you with this beautiful little message, process terminated with status 0, 0 errors, 0 warnings. This means your chef perfectly translated the recipe, the meal was served, and a black console window will pop up proudly displaying your hello world text.
But hey, we're human. What if you made a typo? What if you forgot a semicolon? Let me tell you right now, in C++, missing a semicolon is exactly like forgetting a period at the end of an English sentence. The compiler gets very confused very fast. If you run into a bug, please do not panic at all. It happens to veteran programmers every single day. Just look down at the build log, scroll all the way to the top of that error list, and double-click the very first error message you see. Code blocks is actually super helpful. It will place a little red mark right next to the exact line of code that it thinks is broken. Just investigate that line, correct the syntax, maybe add that missing semicolon or fix a misspelled word, and hit F9 again. If it runs, congratulations, you are now officially debugging.
All right, let's level up. Section 5, formatting text and numbers. With a working program under our belts, let's look at how we can start chaining these commands together to format the visual output in your console and display way more complex information. This wonderfully illustrates just how flexible C++ is. You see, you do not need a completely separate count statement for every single word or number you want to print. You can smoothly chain multiple elements together on a single line. Take a look at this example. We have text strings, which are always enclosed in double quotes, and we have numeric literals, which are just the raw numbers typed out. Notice how we use those stream insertion operators, the double less than signs, as glue. We string together the words today is, then we insert the raw number 15. Then we insert a literal blank space in quotes, and finally, the number 2021. When you run this, the console simply prints it all seamlessly on one line as today is 15/2021. It just reads your code from left to right and pushes it all to the screen.
Now, a quick pro tip on making a new line. We actually have two options in C++. You might look around online and see some code using \n inside the quotes. That is called an escape sequence for a new line. However, for beginners, we strongly recommend using the endl command we learned earlier. Why is that? Well, endl is special because it does two distinct things at once. First, it creates a new line that is perfectly tailored to your specific operating system, whether you're coding on Windows, a Mac, or Linux. But secondly, and more importantly, it guarantees that the output stream is flushed. What that means is it essentially forces the computer to clear out its waiting room and print everything to the screen immediately, right that second. This simple habit prevents some really strange visual bugs from happening when you start building larger, more complex programs later down the line.
Which brings us to the fun part. Section 6, creating console art.
Let's put absolutely everything we've learned together. We're going to use our knowledge of strings, blank spaces, and that endl command to control exactly where characters appear on the screen, allowing us to draw some pretty cool visual patterns. Look closely at this block of code. We have 7 different count statements stacked up, one right after the other. But notice what's inside the quote marks. We aren't writing normal words anymore. Instead, we are strategically placing exact numbers of blank spaces and hash symbols. Look at that first line. It prints a hash, then exactly 9 blank spaces, and then another hash. The line right below it shifts those hashes slightly inward by changing the number of spaces. Line after line, we are manually mapping out a visual shape. And every single time we hit End-L at the end of a line, the computer drops down a row, completely ready to print the next layer of our drawing.
And here is the big reveal. This is the exact visual plot that comes directly from that block of C++ code. As you can see, the resulting console plot perfectly mirrors what you mapped out with your spacing. The reason this works so well is that a standard terminal console uses what's called a monospaced font. That means every single letter, every symbol, and even every blank space takes up the exact same amount of pixel width on your screen. Because of that, you can treat the black console window exactly like a giant grid of graph paper. By counting spaces, you just successfully programmed the computer to draw a giant block letter W.
So here is where it gets really interesting. Once you fully grasp that direct cause and effect relationship between the precise placement of spaces inside your code strings and the final layout popping up on the terminal, the possibilities really open up. How would you scale this up? How would you tackle a larger post-lab project? For instance, using just the basic text symbols available on your keyboard, how would you write a C++ script to draw something complex, like the flag of Bangladesh?
Well, here's exactly how that output could look. By applying the exact same logic we just used for the letter W across multiple, carefully planned count statements, you can generate intricate text art, also known as ASCII art, directly in your console. For this flag pattern, we use repeating rows of equal signs to represent the green rectangular background. To create that prominent red circle in the center, we inject colons into the middle of those text strings. By gradually widening the gap of colons in the middle lines and then carefully tapering them off at the top and bottom rows, it creates a fantastic optical illusion of a rounded circle inside our rigid square text grid. It looks incredibly complex, but under the hood, it's really just a sequence of carefully planned count strings ending with End-L.
Wow, we have covered a lot of ground today. You've successfully set up your lab environment, you installed your IDE and your MinGW compiler, you decoded the fundamental syntax of C++, you learned exactly how to fix bugs, and you just created your very first pieces of digital console art. The foundation has been officially poured. So I leave you with this question. What are you going to build next with these foundational tools? Maybe try spelling out your own name in block letters, or see if you can design a text-based spaceship. The lab is now entirely yours to explore. Thanks for joining me in this explainer, and happy coding!